Okay, so now we are in the fourth lecture. We have already seen about finite and infinite dimensional spaces. So vector spaces we have seen that they can be of two kinds. One, which are finite dimensional, or which are infinite dimensional. So this means which are not finite dimensional. An example of this was the vector space of all polynomials with real coefficients in a single indeterminate x. And examples of this, well, if you take polynomials of degree n, Rn, and so on. We didn't prove, but all the other vector spaces that we saw, like Rx, C01, C101, and so on, they are all of this kind, all infinite dimensional. Rx, R to the power x, where x is any infinite set. Okay, they're all of this kind. Now, what about a finite dimensional vector space? So it means that there is n such that dimension of the vector space V is n. You might be wondering, what is dimension 0? Well, the singleton is a vector space with the very obvious binary operation, star plus star is star, lambda times star is star. There is no other thing that we can define, and this has only one vector, and this vector is its zero vector. So this is a vector space with dimension. Since this is the zero vector, let me write it something simpler. Okay? All right? So that's time. That's the only vector space with the dimension 0. And then what about something else? For anything else, there is a linearly independent set consisting of n vectors such that span of S is V. Then I can get hold, given a linear, and this is the largest size of a linearly independent set. That means if I take any n plus 1 vectors, It's linearly dependent. From this I can construct a basis Remember, basis is not just a set of linearly independent vectors, but along with it, there is a notion of an orientation. In what sense? I'm saying u1 is the first vector of the basis, u2 is the second vector of the basis, and so on. And the moment I have a basis, every x in V has a unique representation say x is x1 times u1, x2 times u2, okay, and we will say that x1 is the u1th coordinate of x, x2 is the u2th coordinate of x, and so on. And this gives rise to a bijective linear transformation. I shall write bijective in this way, which was called the coordinatisation with respect to B. So with respect to each choice of basis, we have a coordinatisation. And what is it? We take x to this is a bijective linear transformation. Okay. So that is what we all established. And I said soliloquy on what does this is geometrization and blah, 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 which I will repeat again. And that is where we are going to start off from today. Now, remember that a linear transformation is a function. Firstly, it's a function between the vector spaces which preserves the vector space operations. Okay. So let's look into this notion of a bijection a little more carefully. And let us look into this notion of bijection a little more carefully. And let's see what is it. So firstly, we start off with a function. So suppose for the time being, we have a function between two sets x and y. It's just a function from the set x to the set y. Let's look at a picture. Now, it takes every object here, every element here, maps to an element here. That's the picture. It could be that it is taking two objects also over here. To the same place. Some of them could be like this only. and there could be some members of Y which are not images. Now, a function can be of three kinds. A function may be one-to-one, which is also said to be injective. And what does it mean? Do we mean by this? It means this situation, the two distinct elements of X going to the same element of Y, having the same image, will not be true. That means distinct elements have distinct images, or in other words, Fx equal to Fx prime would force X is equal to X prime. That is injectivity. It could be, so that is one kind of functions. It could be onto or surjective, which means that there shall be nothing in Y which is free. Everything is an image. That means for all Y in Y, there exists X in X such that Y is equal to Fx. Or it could be both. Which is usually called bijective. So which means that not only does every element in Y is an image of something, but it's the image of one and only one. So that means for each Y in Y, there is a unique X in X such that Y is equal to Fx. So, what's the picture like? What's the picture like of a bijection? So, the bijection, the picture is something like this now. Okay. So, in other words, it means that it is just giving a new labeling. Each X has a new label as a Y, which is Fx, which is its image. So it's something like a new we can think of it as something like a relabeling. Okay. Now let's add that extra condition. So if X and Y were vector spaces and F is a linear transformation which is bijective. So a bijective linear transformation it is a relabeling which preserves the vector space operations. What does it mean? Suppose if x is relabeled as y and x prime is relabeled as y prime, then for any lambda and mu in R, what does lambda x and mu x prime get relabeled to be? It's nothing else but lambda y plus mu y prime. It means that if I have a vector in X, say V, which is a linear combination of some vectors in X, then the image V prime is the linear combination of the image vectors in Y. It therefore means that if I have a subset of X, then, and I consider it's a span, this span is same as the image of this span is nothing else but the span of the image of S. So however may I think of representing facts in the vector space X, they exactly get the same fact with the labels in Y. So if a vector is independent of something, some vectors here, its images are independent of the images there. And similar story goes on. So in other words, as vector spaces, there is no necessity in considering X and Y to be different. Okay? They might look different, they might have different elements, their vector addition and vector scalar multiplication could be different, yes, but as far as vector spaces are concerned, they are same. Let's give an example. I'm sure you must have been wondering about this strange vector space of the first problem set with multiplication as your vectors, as your multiplication as vector addition and powers, x to the power lambda as scalar multiplication. Those of you submitted, most of you could show that this is a vector space and could see that it is nothing else but the properties, the laws of indices. Now, let me give you a second jolt. R is a vector space with its usual addition and multiplication, as we know. And I define my function to be e to the power x. And obviously you know that this is a bijection, and the fact that e to the power x, so it's a way to transform addition to multiplication, tells you that it is bijection and a linear transformation. So the vector space of positive reals with multiplication and power is nonetheless other than the usual familiar vector space of reals. So you see what is this power of, what is this big power of the notion of a bijective linear transformation. Okay? Something so much weird which you must have thought is something very, very familiar now. Okay? indeed the dimension of this is 1, and indeed a vector which spans it is this E. Okay, is a basis, or and all that stuff. Okay, so if I have a finite dimensional vector space, dimension n, and B is a basis, then coming back we have seen this coordinatisation with respect to B as a bijective linear transformation, and then the old story now comes back. So however weird, however strange that vector space V might be, choosing a basis modulo the choice of the basis B, it is giving a very, very familiar presentation in Rn, where n is its dimension. Okay, so that's the whole story, and we shall look into some consequences of this in this lecture again. But before that, we want to emphasize the boon of being a finite dimensional vector space a little further. Okay, so how do we construct? So another thing now is to how to construct linear transformations from a finite dimensional vector space. I am saying it is easy, and as easy as giving a function. So let's see. Suppose V is a vector space and B of finite dimension, and this is a basis. Okay. Now I want to give a linear transformation. So to construct W is another vector space I don't know, it could be finite dimensional, it may not be, and I want to construct okay. I just look into the basis elements. So suppose I give these, suppose I take U1 to say V1, U2 to V2, that means I take any set of n vectors. I am not even saying that the n vectors are distinct. Okay, it could be that they are not distinct even. And I'm saying, so choose so let me put this first, and I put this. Okay, I choose V1, V2, Vn, and then I say that, well, I'll take U1 to V1, U2 to V2, and so on. What do I do with the general X? Aha, here is the boon of coordinatization. Take any X in V. Look into its coordinates. So suppose it is x1, x2, xn. So this means X is actually x1, u1, and so on. Okay. Now, if f were linear, then I have to have fx as f of x1 u1 plus f of x2. So if f were to be linear, then f of x, which is f of x1 u1 x2 u2 but then here is it where I am using the linearity. If this had to be linear, then this must be equal to f of x1 times fu1 x2 times fu2 plus xn times fun. Okay, which is then x1 times v1 plus x2 times v2. And I'm saying this is a linear transformation. Okay, so that's the magic fact. Given a finite dimensional vector space, with dimension of v equals to n, a basis B of V, a vector space W, and vectors there exists a unique linear transformation f from V to W such that fu1 is v1, fu2 is v2, and so on. Thus, in other words, how many linear transformations are there? In as many ways you can assign these n vectors c1, u2, un to vectors of W. So it's enough to construct a function. We often call this as the method of extending or linear extension. Okay? So we will utilize this procedure very closely in the rest of our course. So this is, let me call this is called the method of linear extension. So now let us see some of this application of this. So suppose we start off with a vector space V. It is finite dimensional. So we must have every subspace of V to be finite dimensional. So let's make this observation that observe every subspace of a finite dimensional vector space is finite dimensional. Okay. So what is it that I want to say now is, if I have a linear transformation, so suppose V is a finite dimensional vector space, and dimension of V is n, and F is a linear transformation. For W, I am not saying what is its dimension. It may be infinite dimensional. Given this, I am trying to choose a particular basis, and that is going to tell us many more things. Now remember, in one of the previous assignments, problem sets, I defined this particular set, which is the kernel of F. What is it? Its x belongs to V, says that fx is 0. It's called the kernel of F, and I asked you to show it is a subspace. And it is pretty simple. Why? Suppose if I take x and x prime from kernel of F, lambda and lambda prime from reals, then f of lambda x plus lambda prime x prime, being by linearity, is lambda times fx plus lambda prime f of x prime, but fx and fx prime are both 0, so this is 0. So this shows that lambda x plus lambda prime x prime is also in the kernel, so it's a subset closed under all these. So it's a vector space, vector subspace. Okay. So what we observed, kernel of F is a finite dimensional vector space. And if you go back, is finite dimensional. Not only that, and its dimension is at most as the parent space. So if I have this is a vector space, dimension of V is n, this is subspace, so this tells me U is finite dimensional and dimension of U is less than or equal to n. Okay, and the whole thing is why should it be less? Because what is the dimension? It is the largest size of a linearly independent set. But if I have a set in U which is linearly independent, remember it's a vector subspace. What does linearly independent means? That means if I take a linear combination equated to 0, then that linear combination has to be trivial. So if I take that linearly independent subset of U, take a linear combination, equate it to 0. Being a subspace, its operations are same as in V. So I'm looking at this in U. This same statement also holds in V because U is a subset of V and U is a subspace of V. So therefore, every linear combination of those basis vectors of U equated to 0, well, that's the only way in which it can happen when all the scalars are 0. So it's also linearly independent in V. Okay? And hence, the largest size of a linearly independent set in U cannot exceed the maximum size of a linearly independent set in V. So therefore, the dimension has to be less than or equal to n. Okay? So the kernel of F is finite. So coming back, it's a finite dimensional vector space and its dimension is less than or equal to n. Okay? So let us suppose that the dimension of kernel of F is M, and let say U1 be a basis, a linearly independent set of kernel of F. Remember, I am taking M, its dimension is M. Any M plus 1 vectors in kernel of F is dependent. Okay? And furthermore, what it is saying that these vectors generate all of kernel of F. That means every member of kernel of F is a linear combination of these M vectors. So, here is the picture. So here is my V. Here is kernel of F. And here are my M vectors. Its span is this. Now, if M is then obviously kernel of f is a proper subset of V. So I'll get hold. So there is a um + 1 in V which is not in kernel of f. So if I take an + 1 here, it is like this. It is not in this span of this. So therefore u1 is a linearly independent set. And I can carry on like this at its stage in n minus m steps. So I can say that extend in n minus m steps to a linearly independent subset of V. Since dimension is n, this is a basis. This is the largest linearly independent set, so this gives rise to a basis. Is a basis of V. Okay. Other than via f, irrespective of w, this is the picture. W only entered into the picture via f in kernel of f. There is nothing else, right? Good. So now let us look into this whole thing. So here is u1, u2, um, this is in V. This is F. All of this is taken to 0. Okay? And this is going to some vector, say V1. This is going to some vector, say V2, and this is going to some vector minus m, right? Are they linearly independent? I don't know. Let's see. Let's see if they are linearly independent or not. So the question is, so choose scalars from R such that but this means that lambda 1 f of um plus 1 lambda 2 f of plus 2 lambda n minus m f of this is 0. So this means by linearity f of lambda 1 plus 1 plus lambda 2 plus 2 and so on, lambda n minus m is equal to 0. So therefore this one this vector is in kernel of F. Now let's look into this whole story. The way we selected this basis, these first m vectors u1, u2, um are the only ones which were from kernel of F. These were from kernel of F. And these don't belong to the kernel of F. So therefore, kernel of F being generated by this, each one of these vectors plus 1 and so on is independent of kernel of F. Now you're telling me that you have a linear combination which is in kernel of F. So therefore there are scalars alpha 1, alpha 2, say alpha m from R such that this vector is a linear combination So in particular, you are telling me alpha 1 u1, alpha 2 u2, alpha m um minus lambda 1 plus 1 minus lambda 2 plus 2 and so on minus lambda n minus m is equal to 0. Okay. Now using linear independence of this says alpha 1, alpha 2, alpha m, and therefore lambda 1, lambda 2, lambda n minus m, they are all 0. So it was these steps were actually redundant if you understood that these are independent. So therefore every linear combination of plus 1 to un would be independent of u1 to um. So none of them will belong to kernel of F. So the moment we decided here that this belongs to kernel of F, that's a contradiction. Unless each one of the lambda i's, lambda 1, lambda 2, lambda n minus m is 0. That's the only thing which is there. Okay? There's the only thing, only the 0 vector is common. Okay? So the elaborated proof of this fact that we came from here, we could deduce lambda 1, lambda 2, lambda n minus m is 0, which we will do next time. That elaborated proof is actually over here. Okay? So in future, we are going to use this principle, which I just now, so I put this in a separate color. Okay? So this therefore immediately tells us that So, now let's have a look. Remember, you also told me that the range of f or the image of f is also a vector subspace. And this obviously generated image of f is therefore the span of and we have shown just now that this set is linearly independent. So this gives the basis of okay. This is the basis of image of f. So what is the clear picture therefore? This tells us many things, which we will now slowly formalize. So let us now see what have we done. We started with a linear transformation from a finite dimensional vector space of dimension n to another vector space. We took a very, very special basis of the domain, which is V. We first looked into the kernel of f, which being a subspace of a finite dimensional vector space is obviously finite dimensional and has dimension, say, m, which is less than or equal to n. So we first took a basis of the kernel and then extended that basis to a basis of V. So we are taking a very, very particular basis where the first part actually spans the kernel, and the rest of these vectors do not belong to the kernel, and hence none of the linear combinations of these vectors plus 1 to un can belong to the kernel. Now we are looking into the action of f. Since u1 to um, they all belong to the kernel, they are all taken to 0. Okay? And since these do not belong to the kernel, none of these vectors v1, v2, vn minus m can be the 0 vectors. So they are non-zero vectors. And we showed that v1, v2, vn minus m is linearly dependent, and not only that, it actually spans the image of f. So everything in W which is an image of f, image under f, is actually in the span of v1, v2, vn minus m. Therefore, the image of f is also a finite dimensional vector space. So I don't know about W. The moment the domain is a finite dimensional vector space, its image is also a finite dimensional vector space. And the dimension of the image and the dimension of the kernel add up to the dimension of the domain. So that's a big observation which we now formalize. So given any linear transformation from a finite dimensional vector space, V, the following facts are true. A, kernel of F is a finite dimensional vector subspace of V image of F is a finite dimensional vector subspace of W, and the dimension of the kernel of F plus the dimension of the image of F is dimension of V. Okay? The dimension of the kernel of F is often called the nullity of F. Why? Well, the kernel of F is the subspace of all those vectors from V which are taken to 0, so which are annihilated by F, all the vectors which are annihilated by F or annulled by F, and hence another name for the kernel of F is the null space, and hence the word nullity of F. So how many vectors are taken to the null space, so that the dimension of that is the nullity, and this is often said to be the rank of F. So what does this say? It says nullity of F plus the rank of F is dimension of the domain. And hence this fact, this theorem is also often known as the rank plus nullity theorem. Okay. Another fact about kernels, which is quite interesting, is the following: that obviously, if my linear transformation F be 1-to-1, then only the zero vector, no non-zero vector can be taken to 0. So if F be injective, then kernel of F is 0. So this tells me that the dimension of the kernel of f is 0. Okay. And conversely, suppose that the dimension of the kernel of f is 0, that is the only case when the kernel of f is 0. So, if kernel of f is 0, then if fu is equal to fv, it immediately tells me fu minus fv is 0. So this tells me f of u minus v is 0. This tells me u minus v is in kernel of f, which is exactly the 0 vector. So this tells me u is equal to v. So irrespective of the fact whether v is finite dimensional or not, we have a linear transformation is injective if and only if its kernel of f is the 0 vector. Okay. So what emanates from all of this is, if we have a linear transformation from a finite dimensional vector space, its image is at least finite dimensional. So an interesting case can come up when the codomain is also finite dimensional. Right? So we now look into this special case. So assume f is a linear transformation V is a finite dimensional, V and W are both finite dimensional vector spaces. Okay. Suppose dimension of V is n and B is a basis of V and the dimension of W is n, and say the basis of W. Okay. So what's the scenario? I don't know any thing or any relation between n and m, but at least I know that the vectors fv1 and fv2 and each one of these vectors being in W has coordinates, has their coordinates. In terms of C. Okay. So let me say that, what do I mean? So suppose if I say the coordinates of C of fv1 is, say, a11, a12 and so on. So it means that FV1 is A11 W1 plus A12 W2 plus so on A1M WN. So similarly I will have, say, for each one of them, so in general let me say that the coordinates of VI, FVI is AI1, AI2, AIN, which means that FVI is AI1 W1, AI2 W2, okay. So now I'm saying, so I come up with this strange thing, and so there is a matrix, there is a nice matrix that comes up in which I take say the first column. So I look into this matrix. Okay. So this is a m rows and n column matrix. Okay. So suppose I take any x from V, and suppose the coordinates with respect to B of x is, say, x1, x2, xn from Rn. So what do I mean? X is actually x1 times V1 plus x2 times V2 plus xn times Vn. Let's see now. I'll as if I write this in a proper way, if I write this, if I call this matrix, say, F, okay, so I can see that FV1, if I make this row vector FVN, this is yeah, that doesn't make any sense. So let me write it in this way. If I make this column vector this is actually f of not f of, it's, you call it transpose, f transpose times this. okay, where I obviously mean that you are writing this same thing as like this, but in this strange matrix notation. It's just for a notational convenience. So now let me see. What is f of x? F of x is obviously x1, x2, xn, and this is fv1, fv2, fvn. So this is x1, x2, xn, f the transpose of this times this. Or therefore the coordinates in C of f of x is nothing else. How do I obtain the coordinates? This is nothing else. So if you take the transpose of this is f. Okay, this is coordinates in V of x, f transpose. Okay, to make it look nice, let us make a nice let us make a nice agreement that we will write members of. So this is an agreement. We would write from Rn as columns. Okay, so therefore, under this agreement, the coordinates of C of fx would be f times the coordinates of B of x. Right? So this matrix is actually plain. So once we know this matrix, we know what is it. So what is what f is? So what is happening? Recall that if we had this V, coordinatization by B gives me a geometric representation of V in Rn. The coordinatization with respect to C gives a geometric representation of W in Rm. And you had this linear transformation, and since this is, so you can go back, you can take, so what I did was exactly this. I took a member over here, saw which vector was that member a coordinatization under B4, took its image and then took the coordinates. That's what I did. Exactly so. And that is this linear transformation then, which takes x. What is f bar of x doing? It is taking to fx, which is the matrix multiplication. Okay? So f bar of x, let me write it as is the matrix F times this. Okay, so this is the corresponding linear transformation. So F bar, this is a linear transformation corresponding to F. Okay, so therefore, by virtue of the fact that these are bijections, there can exist only one linear transformation such that F bar of coordinatization of V is same as this, which is this equation. Okay, coordinates on C of Fx is F bar of coordinates of x. Okay, so therefore this matrix which we took is the matrix which represents that linear transformation. Okay, and we often call F as the matrix representation of F, and we shall henceforth denote it by MAT of F. Okay, so how is MAT of F computed? It is an M cross N matrix, so which is dimension of the codomain cross the dimension of the domain. So you look into and since I would just not write MAT of F, since it is corresponding from the basis B, so I'll write MAT B to C of F. Okay, so which means the matrix representation of F with respect to the basis B on domain and C on codomain. Okay, so this is the matrix representation of, and that matrix shall henceforth be denoted by this symbol. So how is this matrix computed? Let's look into it. So you will have this linear transformation. Dimension of V is N, dimension of W is M, B is a basis and C is a basis. How do I compute this? So matrix from B to C of F, the first row is coordinates in C of FV1, coordinates of C in FV2, and so on. This is coordinates of C of FVN. So it's a matrix whose columns are the coordinates of the images of the basis vectors with respect to it. Okay? So that's the whole story. a particular case, a very special case, when V and W are the same vector spaces, okay, and B and C are two bases. Of V. This is often called the change of basis. And then what you are doing? So, remember, I have said from the linear extension principle, the moment I tell where the basis vectors go, that's enough. So my linear transformation from V to W is like this. V1, so that there are two bases, and W1, W2, Wn. Okay, I'm saying F takes V1 to W1, V2 to W2, and Vn to Wn. So obviously, I know that the kernel of F, so therefore the kernel of F is 0, that is F is injective, and the dimension, the image of F has dimension n, so it is F is surjective. So it says that F is bijective. It's a bijective linear transformation. By the method of extension, you know how would you extend it to anything. So the matrix what is this? So this is coordinates in C of V1, F of V1, let's look into this. So F of V1 is actually W1. It's quite interesting if I look into this. And what is this? This is obviously 1 0 0 0 0. So this is obviously In. Okay, but we missed a little bit. It's not actually the matrix of this, the change of. So what are we doing? So we want to find. So the change of basis from B to C, that means if you are given the coordinates in terms of B, I want to find the coordinates in terms of C. Okay? So instead, so what have I to do? So given coordinates of a vector, need to find coordinates with respect to C of x, the same x, not of fx. So my linear transformation is not of not f, not this particular f. So I want to find the, so x is actually being taken to x. So I want to find this of the identity linear transformation. Okay? So the linear transformation over here is from v to v, which is taking x and keeping it to x. That's the identity linear transformation. Okay? So the linear transformation is the required So I need to find out this of 1v. So this is coordinates of C of v1, coordinates of C, v2, and so on. This is an n cross n matrix, and this is often denoted instead by this symbol P B to C. It is called the change of basis matrix. Okay? Change of basis matrix. We will see more of this in the assignments.